DeCastleJoe subdivision algorithm, which works like this. Suppose you have a Beszier curve with 4 points. So it's gonna note something like that. Frowny face, gets you laughing about. And suppose you decide that you want more precision. You want to subdivide this curve in half so that you have 2 curves. And then you can, individually mess with them. Maybe you want to subdivide them again so you have 4 curves. Because right now, this is all you have, and if you mess with any of the 4 control points, it moves the whole curve. But maybe you just want to move this part of the curve without moving this part. Well, then you could subdivide it and move this curve up a bit while leaving this one where it is. Right? So maybe you want to subdivide it. So DeCastleJoe said to subdivide the curve in half, find a point halfway between the first 2 control points and another point halfway between the second 2 control points and another point halfway between the third 2 control points. And then find a point halfway between those 2 control points and a point halfway between those 2 control points. And then find a point halfway between those halfways. And let me erase my original curve because I drew it wrong. Looked. The new control points for the subdivided curves are here, because it starts at the same spot, here, here, and here. For the second curve, they are here, 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 and here. And voila, you now have 2 curves who together cover the same arc as the original curve did. Right? So that's, if you're going to make a drawing package, you'd probably want to allow the user to be able to subdivide a curve so that they could have individual control over here. They wanted to mess with half of it and leave the other half alone. Now, you wouldn't have to divide it at 0.5. I could say, I like most of the curve, but I want to divide it at 0.9. So then I would find a point 9/10 of the way from here to here. And 9/10 of the way from here to here. And 9/10 of the way from here to here. And then I would find a point 9/10 of the way from here to here. And 9/10 of the way from here to here. And then I would find a point 9/10 of the way from there to there. And then the 2 new Beszier curves are this point this point, and this point for the first curve. And then the second one shares that one and goes those 4 points for the second one. So then the first curve would go like that, the second one would go like that, and again, together they would match the original curve. So you can subdivide it any way you want. Now here's another observation. By subdividing it at 0.5, I basically evaluated it at 0.5. By subdividing it at 0.9, that point is the same as if I evaluated it at 0.5. So while Mr. Beszier said to use this fancy-dancy formula, a point evaluated at a t between 0 and 1 is 0.0 times 1 minus t cubed, on and on and on. We've seen that formula. Mr. DeCastle-Joe, on the other hand, said if you want to evaluate it at some t, whatever the t is, 0.3, go 0.3 of the way from there to there, 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 and that's it. You don't need to do this formula. Cool, huh? So it's a series of linear interpolations equals this cubic formula. And Mr. DeCastle-Joe also said, he made the observation that the control polygon itself, the control polygon would be just connecting control point 0 to 1 to 2 to 3. The control polygon itself approximates the curve, not very closely, but notice after one subdivision, this control polygon is closer to this curve, and this control polygon is closer to this curve. If I subdivide it again, then the control polygon would be more like this, and this one would be more like this, and it would be very much closer to the curve. And so DeCastle-Joe says, hey, just subdivide the curve into 2, 4, maybe 8 pieces, and then you don't even need to figure out points on the curve. Just draw the control polygon, and that will hug the curve. That's close enough. Subdivide it twice, 4, 8 times, connect the control polygons, and that'll be close enough to the curve. So that's his idea of how to draw them. Yeah.
Does this work with weighted curves?
That is a good question. I'm gonna say no. Most of the stuff Most of the cool stuff you can do with Beszier curves does not work if they're weighted. Unfortunately. Okay. What is the difference between interpolating curves versus approximating curves? Well, interpolate means that the artist who's using your package gives you points and they expect the curve to go through them. Interpolate means hit every point, or at least some of them. Approximate means if they give you some points, they want it to kind of pull toward the points. So a Beszier curve is kind of a mix between the two. It interpolates the first point and the last point and approximates the middle two. That seems to be about the best compromise or mixture for modeling. At first, artists don't like that. They're like, if I give you 4 points, I want you to go through them all. But what happens is, mathematically, if you try to force it to go through 4 points, it won't do that. It'll do this. You know, something like that. There, it did it mathematically. So it's much harder to get what you want if you're trying to force it to go through 4 points than if you do it the Beszier way and let it naturally move toward the middle points. Derivatives. You all know how to take the derivative of a regular y equals x cubed kind of function, ax cubed plus bx squared plus cx plus d, if you've had calculus. The derivative, which we'll call y prime, or derivative of y with respect to x, is 3ax squared plus 2bx plus c. Maybe you're looking at this one, thinking 3p1, 1 minus t squared t and so forth. How in the heck do I take the derivative of that as a function of t? Let's see, if we got 2 things with t, it's first times the derivative of the second plus second times the derivative of the first, and it starts to look like a mess. But in fact, it's super easy. The derivative of a degree 3 Beszier curve is simply a degree 2 Beszier curve, and to find the values of the degree 2 Beszier curve, this is, I guess, where Kenneth Adamson carries some clout when he says you should just treat points and vectors all the same. Because if you find this vector, and this vector, and this vector, v1, v2, v3, those are the points that you use to construct the derivative curve. So the derivative curve is the derivative curve, we'll call it, you start with this one, and the derivative curve, p prime of t, is v1, I should have probably called it v0, V1 and V2. V1 times 1 minus t squared plus 2 V2, 1 minus t times t, plus V2 t squared. Except you have to multiply the whole thing times 3. V0, V1, V2. So it's super easy to find the derivative curve. Just a V2 Beszier curve tells you all the derivatives of the original Beszier curve. Cool. I have to keep saying cool, because I don't think you guys are appreciating this as much as you should be. Okay, B-splines. So I mentioned before that with Beszier and de Castelgio, these original guys, the curves didn't provide for C2 continuity. That is, continuousness in the second derivative. You could get continuousness in the first derivative. If these are my 4 control points of the first curve, I simply start the second curve here, and the second point of it needs to be collinear with this one, and this one. And then I can put the other 2 wherever I want, and I'll have C1 continuity. Position continuity and tangent continuity. But I won't have C2 or curvature continuity. And you basically can't. It's extremely difficult with Beszier curves. So B-splines were invented to get curvature continuity. So at the connection points between B-spline pieces, you're always C2 continuous. And we saw an example of it last time on the computer with the student that implemented it. And I'll show you real quick how you can implement it. You still have the idea that 4 points define a piece of curve, but instead of starting at the first point and ending at the last point, it starts roughly at the second point and goes roughly to the third point and kind of pulls toward the first and kind of pulls to the last. But it doesn't interpolate any of them. It just approximates all of them. And then if I wanted to add another piece of curve, I don't add 4 more of these, I just add 1 more. Because every piece of B-spline shares 3 control points out of 4 with the previous neighbor. And it's this sharing of 3 or 4 control points that gets you C2 continuity. So this piece uses these 4. The next piece will use this one, this one, this one, and this one. And the curve will be roughly between the middle 2 of the 4. And at that piece, it's very continuous looking. What? Did I draw something again that I'm not aware of?
Just this thing goes.
So the next piece, 5, I would add a 6th control point, and then it would roughly go between the last 2 of the last 4. I want to add another piece, put it there. I want to add another piece, put it there, and so on and so forth. And you can keep going as far as you want. And again, you're not going to be interpolating any of these points, but if the artist plays with it and gets used to it, it's very intuitive to pull these in and out, and the curve will just pull in and out with it. So it's not super precise. They can't say make it right here. But if they want it to go through a point, they can just visually look and pull this out until it goes through the thing they want it to go through. So it turns out to be very intuitive, and they can make it as long as they want. And if they want it to start at a certain point, then again, they just mess with these two until it starts at whatever point they wanted it to start at. So that's the idea of B-splines, is you can hook a bunch of them together, and unlike Beziers that are only C1 continuous, these are guaranteed to be C2 continuous. 4 minutes left. What are non-uniform B-splines? Well, first of all, back to B-splines. With a Bezier curve, it's defined between 0 and 1. With these things, maybe it's here it's 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on. So I could, for example, use this to define an animation. I want the rabbit to run here and here, or the car, or the airplane, or whatever it is. Okay. That's how it's defined. 1 second here, 1 second here, 0, 1, 2, 3, 4, 5. But what if I wanted the rabbit to go from here to here in 0.5 seconds? And from here to here, I want it to be here at 0.5 and here at 1.3 and here at 2.6 or whatever, different values. That's what the non-uniform does for you. It allows you to change the parameterization. So these B-splines, you could nickname them uniform B-splines because the connection points are always at even intervals. 0, 1, 2, 3. Non-uniform, I can put any values I want here, as long as they're incrementing in time. Change the parameterization, which can come in handy for having something stopped and then speed up and then slow down, whatever you want. What is a NURB? NUB stands for non-uniform B-spline. What do we get with the R? Remember I said weighted Bezier curves are often called rational because they have a denominator. So a NURB is, hey, let's put everything in the kitchen sink together. Let's have a B-spline that can have non-uniform parameterization, and let's throw in weights to all these points too. So I can leave them where they are, but say, oh, and pull more toward this, and pull less toward this. So NURB is everything in the kitchen sink thrown in with it. Now let's not worry about Remy curves. Nobody cares about those nowadays. And then, again, in real life, people care more about making surfaces than curves. Because in real life, if we make something, it's